Hey, Algebra 2 friends, here we are. We're in chapter 9, section 9.1. We're going to be looking at multiplying and dividing rational expressions. Well, the first thing we want to do is get to some vocabulary. The vocabulary for today would be rational expression and complex fraction. A rational expression is something that you know about. Now, here's the thing. The word ratio is in there. So it's an expression that can be written as a ratio or as a rational number. So we know that a rational number is a ratio of integers, right? So any number that can be written as a ratio of integers or a fraction with a numerator that's an integer and a denominator that's an integer is a rational number, and a rational expression is similar in that if you have an expression that's written as a ratio of two other expressions, that's a rational expression. For example, these two representations or these two expressions are rational expressions as they're written in fraction form. So that's a rational expression. And we brought up the idea of fractions. So you know we're going to be talking about fractions today to a certain extent, as you can see that this is a fractional expression. But what's a complex fraction? A complex fraction is when you have a fraction within a fraction. So for example, a complex fraction could be written as 3 over 4 over 5 over 7. That's complex. It doesn't seem that complex. But when we get it into x plus 2 over 3 minus 5x over maybe 7x over, I don't know, x squared minus 1, then you're like, okay, this is complicated. So this is what complex fractions look like, and we'll have some strategies. Sorry about that. We'll have some strategies to deal with them. So this first example requires us to simplify a rational expression. And really, simplifying a rational expression is a lot like what you all are used to, where we make sure the numerator and the denominators are factored completely, and after they're factored, we kind of have a canceling party. So right now, you notice that the numerator of this rational expression is factored as completely as possible. So x minus 5 is just one of the factors, x and 2. Here we have x minus 5 in the denominator, so we see some potential for canceling. And then we're going to factor x squared minus 1. X squared minus 1 is a difference of squares. And if you remember a couple chapters back, we would factor that like this. What we're remembering here is that a squared minus b squared, difference of squares, is equal to, will always be factored in a way that we can write it as a plus b times a minus b. Okay, with that out of the way, let's continue on. So now that we have everything factored, we can cancel. We can cancel out x minus 5 in the numerator and the denominator, and we can't cancel anything else. We cannot cancel the x's, though some of you might want to try that. We can't do it because the x in this case isn't being multiplied. It's not one of the factors. So our final answer can be written in the following way, where 2x is divided by x plus 1, x minus 1. This next question is interesting. It says, under what conditions is this expression undefined? We know that things are undefined when we divide by 0. So we have to consider not just our final expression, but what happened before. Because if this was a 0 in the denominator and a 0 in the numerator, we cannot cancel them. That's not okay because we don't divide by 0. So what we do is we go back to the original problem and we consider all of the factors of the denominator. In this case, we had x minus 5. We also had x plus 1 and x minus 1. We consider what would happen if each of those factors were 0. So let me change the way this looks a little bit. So we set each of them equal to 0. And when we do that, we can see that the excluded values, or the values that we know this expression cannot be, would be anything that would make these expressions 0. So x cannot equal 5, or in this case, -1, or in this final case, a +1. A very important skill that we need to learn as we're taking standardized tests is the process of elimination. So I know you guys would know how to answer this question. In this problem, we're asked to figure out for what values of x is it will the answer be unidentified or undefined, pardon me. So what you would do is take the denominator, factor it, set it equal to 0, boom. But how can you use the answer choices to help you? What you can do is look carefully at the answer choices and see which ones don't make any sense. Well, clearly 0 doesn't. You can mentally plug in 0 and see that by plugging in 0, we don't get a 0 in the denominator, which is the thing we're fearful of. So automatically we can eliminate that. And another hint is you can see that -4 will definitely work. How can you tell negative 4 will work? Well, it's in all the other answer choices. So the next thing we can do is check to see if 3 or negative 3 works. So if 3 works, we know we are not going to have 3 zeros in the denominator, then we're good. And if 3 doesn't work, then we're going to know that this is the answer. Did you see how I did that? Now, I don't know the answer because I didn't try the problem, but I want you to think about the way we eliminate it without doing any work at all. And what I'm saying is we can substitute in just one value. Again, 0 clearly doesn't work. We can mentally throw that in. Since all of the other answer choices have negative 4, we know negative 4 works. The only question is, does negative 3 work or 3? Sorry about that. So depending on which one works, if negative 3 does work, then we're good. We know 3 doesn't. And if 3 works, then we're good. We know negative 3 does. I think I said that right. Anyway, I'm going to do the problem the way I want to. So as a math teacher, I would want factoring to be a pretty easy thing for you to do. So when we factor this quickly, x plus 4, x plus 3, and just the denominator, because that's where our undefined terms come from. When we factor it quickly, we can see that, yes, negative 4 would make this 0, but also negative 3. So this is indeed the answer. In example 3, we have an idea that we can simplify by factoring out a negative 1. And so what we'll do is we'll factor as usual, but we'll see how this idea of negative 1 will come into play. So I'm going to factor the numerator completely by factoring out z squared. What I'm left with is w minus 1. I'm going to factor out z squared out of the denominator as well. And clearly, actually z to the third power. Wasn't being careful there, my bad. So factor out z to the third power. Let me make it look more z-like. And I'm left with 1 minus w. Now, clearly, it's pretty simple for me to simplify this part. I'm going to be left with no z's at the top and 1 z at the bottom. But the question is, what's going on with w minus 1 and 1 minus w? The fact of the matter is that if I had w minus 1 and I multiplied it by negative 1, these two would be equal. Think about it. Distributive property, switches the signs. Sometimes I call it the power of negative 1. It kind of makes everything exactly the opposite. So when I do that, I get 1 minus w. So if that's the case, w minus 1 divided by 1 minus w must be negative 1. So technically, I'm factoring out a negative 1 here so I can have an identical factor in the numerator and the denominator. And when I do that, I can cancel it out. So if you notice that you need a little flip-flopping happen, if you realize that the signs, everything would cancel out, if you can just change the signs, know that you can factor out a negative 1. So in example 4, we're going to be multiplying rational expressions. And if you remember multiplying fractions, if you have a fraction a over b times another fraction c over d, you might remember that you just find the product of the numerator and the product of the denominator and you're done. So when I do these problems, sometimes I just draw a big line through all of it and multiply everything together and cancel. So that's what we're going to do here, but I'll try to make it very, very plain. So if I'm looking at this problem, I see I have a 4 and a 15, a b and another b. I'm telling you, I would probably not write this out, but I want to do it so it's clear. And then here in the denominator, it's like a 5 times a b times a 16 times an a, another a, and another a. So what I'm doing is representing a very factored out form, at least of the variables. I could have changed this to 2 times 2 and this 3 times 5, but I'm going to save that because I think you can do this without me doing all of that. What we'll do now that we've got it multiplied together is we're going to cancel. So the b's, this b will cancel with this one. This a will cancel with one of these down here. 4 will cancel out of 4 inside of 16, where 5 will cancel out of 5 inside of 15, leaving a 3. So in the numerator, what we're left with is 3b, and in the denominator, we're left with 4a squared. And that's how you simplify that's how you simplify rational expressions when you're multiplying them. Let's look at this guy. This time I'm not going to write it out. Let's see how it goes. So again, I'm looking at this as one large fraction, so everything's being multiplied together. And okay, for the sake of the visually troubled like myself, I'm going to make this a little bit bigger because I like to see it. So what I'm going to do is I'm going to start canceling in the same way. And I didn't factor, but I think we can handle this. So if I look and I see, okay, well, 5 goes into 15 3 times, and well, 3 goes into 12 4 times, and 3 goes into itself once. 4 goes into 8 2 times, and 4 goes into itself once, we've really whittled down all of the coefficients to just 2. So our answer will only have a 2 in it so far. Now let's see what happens with the variables. So now I've got one s here, and I'm going to cancel out the squared, so I only have one s in the denominator. But now I've got, I see another s here, so all the s's have gone away. Now we'll deal with the r's. One r is here, so I'm going to cancel that out and get rid of that one, so I've canceled out an r. And finally, these t squareds need to cancel into this t to the third power to leave a t in the denominator. So what I'm left with in the denominator is an r and a t. In the numerator, everything else has been canceled out aside from this 2. So my final answer is 2 over RT. So division is going to be similar. So you remember this. When we divide fractions, we start off with the division and then we change it to multiplication and we flip the fraction after the division sign, or now after the multiplication sign. So we take the reciprocal and then basically we proceed just like it's a multiplication problem. We're going to do that here as well. So the first thing I want to do is start off by rewriting this division problem as a multiplication problem as our formula suggests. So now we'll exchange this problem for this problem. And I smushed all of the numerator together and the denominator together so we have this one big fraction. Now it's time to cancel, and I would suggest you try to cancel carefully. This is not my first rodeo with this problem, and it's not a hard problem, but I realize that my handwriting and all these other things keep getting in the way. So I'm choosing a different color to cancel with, and I'm going to just be careful. So maybe an organized way of doing it would be to start with the numbers. So notice I canceled 2 into both 2 and 4 and 5 into both 5 and 15. And so now I'm going to get to my letters and see if that works out nicely. The b to the third powers go away, which is good. I've got x squared up here that's going to turn into x as I cancel out this x in the denominator. Over here, I've got one y that I'm getting rid of in order to leave one y in the denominator. And finally, this a is going away in order for me to just have 2 a's in the denominator. So now that I'm looking at what's left, I see I have a 2 and I have an x in the numerator left. And in the denominator, I have a 3, an a squared, and a y. And I feel like finally that's probably a more clear way of doing it. I know you haven't seen the other mess ups, but trust me, it was bad. Let's go ahead and look at another example, guys. All right, so hopefully this is starting to make a lot of sense. You know what the key things are. If it's multiplication, you could look at it as one big fraction. But since you're multiplying everything or thinking about it as things being multiplied together, I would not suggest you FOIL. Remember, our goal is to factor. So I'm going to factor the numerator and denominator completely here. And this is what we get when we factor completely. And finally, we're just going to do what we've been doing. We're going to cancel out what we can. So common factors can be canceled out. And we see we have x plus 1, x plus 1, x minus 2, x minus 2, which leaves us with 3 times the quantity of x plus 4 over x plus 3. Let's do the same thing to this one down here. First, we're going to change it to a multiplication problem. Now that we've done that, we're going to factor everything, make it all one big fraction. Now that we've got that factoring out of the way, notice we have that difference of squares again. We're just going to cancel. These guys go away, these guys go away, and our final answer is a plus 2 over a plus 4. Let's get ready for our final example. There are a number of ways of dealing with complex fractions, and no way is better than any way that makes sense to you. But what I'm going to do first, you can see this is the fraction bar with 2 other fractions on top, so I'm going to factor everything so we can get a better look at what's going on. So the factored form here is kind of what you think. Here we've got difference of squares, but what we're seeing is that this is a division problem. And so you know the division of fractions can be written as the multiplication of fractions, so the number at the top stays the same, but then we take the reciprocal of the number that's being divided. Clearly we can do some canceling here. Let me use my trusty red pen. And then what we're left with is this right here, where we have this factor that looks very similar to this factor. And you might remember we just talked about it. When you see something that looks like it would be great if you could flip-flop it, factor out a -1. So I know that these guys will divide into each other and not cancel, but leave a -1. All right, so we have r plus 5s. And that's it for our lesson, and that's it for this problem. Let me know if there's any questions. I will happily explain or talk to you as soon as we get a chance to get together. Take it easy, guys. Bye-bye.